Okay, so now we're going to go into detail and go over specific examples of how gene regulation works in bacteria. So it's important to note that this idea of regulation and enzyme adaptation came from some studies by Jacob and Monod. So the idea of enzyme adaptation means that enzymes appear in a cell only after the substrate that said enzyme needs is present. So if the substrate is there, the enzyme is produced. If the substrate is not there, the enzyme is not produced. And this they called enzyme adaptation. And it makes perfect sense. So remember, we're looking back to what's energetically favorable. So why would we make an enzyme if its substrate isn't there? The enzyme is just going to be there doing nothing. Okay, so think back to 102 and substrate and enzymes. So in bacteria, what is the preferred energy source? And think about humans. What is our cell's preferred energy source? You know, your automatic answer should be glucose. So we have mechanisms to utilize that glucose. But if lactose is present, well, we have to use what we can. So now we're going to start to produce the enzyme to metabolize that lactose. So lactose is arranged in an operon. So remember, single promoter and many genes. We have the cap site, the promoter, the operator. Then we have 3 genes like Z, Y, and A. They can encode enzymes that function in the lac operon. Outside of the lac operon, we have a regulatory gene. So we have LAC-L, which is under the I promoter, and this is a separate entity, and its job is to produce the lac repressor. Okay? So in the lac operon, we are making lactose permease. Lactose permease allows for lactose to come into the cell. Then we have our beta-galactosidase. This is encoded by the LAC-Z. Its job is to cleave lactose. So we're going to break it down into its subunits of galactose and glucose. It can also change lactose into allolactose, which is similar, structurally similar to lactose. Okay? And allolactose's job is to serve as an effector molecule. So the lac operon is negative inducible. Negative means it has a repressor. Inducible, off, but you can turn it on. Okay? And this depends on if you have lactose present or not. So if we do not have lactose present, then here this is our polymerase that binds to our promoter, but this is our repressor that binds to the operator. Now remember that the LAC-L regulatory gene is outside of the operon. So this has been transcribed. It makes this lac repressor. The lac repressor binds to the operator. No lactose, no need to produce these genes. When lactose is present now, so we still have this LAC-L that made our repressor, but this allolactose, so remember, structurally similar to lactose, and is an effector, binds to our repressor, making a conformational change that doesn't allow our repressor to bind to the operator. Therefore, this lac operon is being created. Okay? So, no lactose, repressor is bound to the operator. Lactose, no repressor on the operator, we can transcribe. Okay? And now this is a dynamic process. So when we talk about gene expression, we usually say turning things on or off. We probably should say turning things like increasing or decreasing, because these things are still, remember that basal level, so they're still being produced at low levels. So under normal circumstances, we have our enzymes here at very low levels. Our repressor is bound to our operator. Now we're in an area where we have all this lactose in abundance outside of our cell. Okay? So it's going to start to come into our cell through the permease. As it comes in, it's going to be converted into allolactose that's going to bind to the repressor and knock it off of the lac operon. Now we are able to ramp up production. So now you see all these permeases in the membrane allowing us to take in all the lactose that's out there. Okay? So this is just going, going, going. Well, we're moving very fast and we're using it up. Now it's no longer there, right? So now it's going to fall off of our repressor. Our repressor has a conformational change. Now it can bind to the operator again, and now we're going to start to degrade all these proteins involved in the metabolism of lactose because we don't need them. And then this can go on and on based on the abundance or depletion of lactose in our environment. But it's not that simple, okay? So two conditions have to be met in order for us to make Operon genes. The first one we know is you have to have lactose present. Well, the second one is you can't have glucose present because remember, glucose is the preferred energy source. So if glucose and lactose are present, we're going to use that glucose, okay? So it's positive inducible. Positive requires an activator. Inducible off, but we can turn it on, okay? And now the positive depends on glucose. All right, so we're going to put them both together. So in a condition where we have no lactose and no glucose, so remember, lactose controls the repressor, glucose controls the activator. No lactose, our repressor is bound. No glucose, our activator is also bound. But our polymerase isn't getting in here, so there's no transcription occurring. We have glucose, but no lactose. So we have glucose, so the activator is not on. And we don't have lactose, so our repressor is on, and there's no transcription. Now, we have lactose and we have glucose present. So we have lactose, so allolactose binds, causes the repressor to knock off. We have glucose, so the cap is not on, but the caps are activated. The activator is not on the activator site, so no transcription or these low levels. We have lactose and we don't have glucose. No lactose means our repressor comes off. Sorry, lactose means our repressor comes off. No glucose means our cap goes on. Now we're ramping up production because we don't have our preferred energy source of glucose and we do have lactose, so we want to use it, okay? So those are the conditions that are necessary for the Operon. You have to have lactose and you cannot have glucose to ramp up production of the Operon. And then the last layer of complexity with this is, so the more and more people have started to figure out, they now know that there are multiple operators that are involved in controlling the Operon. So we have these operators O3, O1, and O2. And they, through studies of knocking some of these out, they realize that having all three gives you the best repression of lactose. And then they can see how many base pairs these things are from each other. And they found out that our repressor tends to bind to 3 and 1 or 1 and 2, but not 3 to 2 based on the difference, okay? So we can bind to 3 and 1. They're close together. We can cause our DNA to have a change to bind to 1 and 2, but we can't bind to 2 and 3 at the same time, okay? That's the Operon. So what do you take away from this? That the idea that this Operon is positive and negative inducible, meaning it has a repressor and an activator, and it's usually off, but you can turn it on depending on conditions. And those conditions are no glucose and an abundance of lactose.